get handed like a really dense document, maybe it's a syllabus for school or guidelines for something complex, it feels like this secret code, this PDF that's supposed to unlock a whole subject. But it's not just what you learn, it's how it's all put together, how they measure if you actually, you know, get it. Well, today, that's exactly what we're tackling. We're doing a deep dive into the assessment guidelines for physical sciences. Our goal is to take this official looking document and break it down. We want to see not just the topics, but the thinking behind how understanding is tested and why that actually matters for you. Our source doc today is called SAGS Physics 2024.pdf. SAGS. That stands for Subject Assessment Guidelines. So it's the official playbook for physical sciences assessment. Okay, let's unpack this. How does this entire subject get measured and evaluated? It's not just a single final exam, is it?
No, not at all. You've hit on a key point. It's much more layered than that. The assessment for physical sciences basically rests on two main pillars. You've got your formal exams, and then a really important school-based assessment part. So there's paper one, that's all physics, and paper two, which covers chemistry.
Right.
And they're pretty hefty. Each one is 3 hours long, and they start out being marked out of 200 marks.
200. Wow.
Yeah, but then those marks get scaled down to 150 for the final calculation.
Okay, scale to 150. Got it.
But here's a really crucial piece. The school-based assessment, or SBA, that adds another 100 marks to the pot.
100 marks just from the SBA.
Exactly, which works out to be a full 25% of the total grade for the National Senior Certificate. So the whole subject is out of 400 marks, and a quarter of that comes from work done throughout the year.
A quarter. That's significant.
Yeah.
Tells you it's not all riding on those final exams.
Precisely. It encourages consistent effort. And just a note on the exams themselves, they use various question types, but multiple choice questions. They make up a maximum of only 10% of the marks.
Only 10% multiple choice. Interesting. So they're really testing deeper understanding.
That's the idea. This balance between the big exams and the ongoing SBA is meant to give a more holistic picture of what a student knows and can do.
That makes sense. So if that's the overall structure, let's zoom in on the content. What actually gets covered in these papers? Looking at the breakdowns, what jumps out? Where does the curriculum put its weight?
Yeah, looking at the weighting is really revealing. For physics, that's paper one. The biggest slice by far goes to kinematics, motion in one dimension. That's about 50 marks, roughly 25% of the paper.
25% just on motion.
Mm-hmm. It suggests that really mastering how things move, the language of it, is seen as fundamental, like the absolute bedrock. Then you've got Newton's laws and applications, and also momentum, impulse, work, energy, and power. Those are chunked together, each around 30 marks or 15%.
Okay, so classical mechanics is really dominant in physics.
Definitely. And then you have areas like gravitational and electric fields at about 10%, electric circuits at 15%, electrodynamics around 12%, and photons and electrons making up the last 8% or so.
Got it. And what about chemistry? Paper two. Where's the focus there?
Chemistry has a slightly different feel. Two areas really stand out: electrochemistry and organic chemistry. Both are weighted at 40 marks each.
40 marks each, so that's 20% per topic.
Exactly, 20% each. That's a huge emphasis. It suggests these topics might require pulling together lots of different concepts or involve more complex problem solving. Organic, especially, often needs both memorization and understanding principles.
Like structures and reactions.
Yeah. Then you have quantitative chemistry at 15%, chemical bonding at 10%, energy change and rates also at 10%, and chemical equilibrium and acids and bases both around 12.5%.
So looking at these weightings, you can really see where you need to focus your energy. Any surprises there or patterns that seem particularly important?
Well, the big takeaway is that breadth and depth are needed. But the heavy weighting on kinematics and physics and those big chunks for electrochemistry and organic and chemistry really signals their foundational or perhaps synthesizing importance in the curriculum. It definitely guides where study time is best spent.
Okay, that makes sense for what is taught. But you mentioned earlier they're testing deeper understanding. This document talks about different cognitive levels. That sounds important.
It really is. This is maybe the most insightful part of the guidelines, I think. The assessments aren't just about remembering facts. They're deliberately structured across 4 cognitive levels, testing progressively deeper understanding.
4 levels. And how are they weighted?
Okay, so level 1 is knowledge and recall, just basic facts. This is only 15% for both physics and chemistry.
Only 15% for just knowing stuff.
Right, it sends a clear message. Level 2 is comprehension and routine exercises. This is about understanding concepts and doing simple standard problems. It's weighted at 35% for physics and 40% for chemistry.
So a bigger chunk there. understanding the basics and applying them simply.
Exactly. Then comes level 3, application and analysis. This is where it gets more complex, interpreting situations, applying knowledge in new contexts, maybe doing 2 or 3 step calculations. This is weighted at 40% for physics and 35% for chemistry, a really significant portion.
40%. Okay, so that's the core of the assessment, really applying the knowledge.
You could say that. And finally, level 4 is synthesis and evaluation. This is the top tier, only 10% for both subjects. Here, you're pulling together ideas from different areas, evaluating scenarios, often doing complex calculations without much guidance.
So what does this all mean? It's clear they're not just looking for rote memorization. Can you give some concrete examples? Like, what does a level 1 question look like versus a level 4?
Sure. A level 1 question is super straightforward, like define acceleration, or maybe name the part in a DC motor that ensures continuous rotation. Just recall.
Okay, simple definition or identification.
Right. Level 2 comprehension might be something like explain why reaction rate increases when acid concentration increases. Or how does the speed of ejected photoelectrons change if you increase the light's frequency? It asks for an explanation or a simple relationship, also includes basic one-step calculations.
Makes sense. Understanding the why or a direct consequence.
hmm Now, level 3, application and analysis, steps it up. Imagine you're given a circuit diagram. The question might be, determine the effect on the voltmeter reading across the battery if you change something in the external circuit. You have to analyze the change and apply circuit rules. Or maybe calculate the EMF of a galvanic cell given a diagram. It requires interpretation and applying principles in a specific, maybe slightly unfamiliar context, often 2 or 3 steps.
Okay, definitely more involved applying the rules.
And level 4, synthesis and evaluation. This is where you really have to think like a scientist. Remember that car and truck collision example?
Yeah, the one with different masses hitting each other.
Exactly. Asking which driver is likely to be more severely injured and why, referring to acceleration and velocity. That's level 4. You have to bring together Newton's laws, force, mass, acceleration, maybe even impulse concepts, and then evaluate the outcome. There's no single formula. You synthesize multiple ideas. Or maybe analyzing a complex graph showing reaction rate changing over time and explaining the effect of some change on, say, the pH.
Wow, that car truck example really shows the depth. You have to connect so many dots.
Precisely. And what's fascinating is how explicitly the curriculum aims to build these higher order skills. It's not just about passing physics or chemistry, it's training you to analyze, synthesize, evaluate the core skills of scientific thinking.
So it's about the thinking process, not just the final answer sometimes.
Very much so. Now, to tackle these problems, especially the more complex ones, you're not expected to have everything memorized.
Right, you mentioned a data sheet.
Yes, exactly. You get an information pamphlet or a data sheet. It's a toolkit, really. It has formula and equations, key physical constants, speed of light, Planck's constant, gravitational constant, things like that.
Okay.
It also includes tables like standard electrode potentials for chemistry and, of course, the periodic table. But here's an interesting point from the guidelines. The formula aren't just for plugging in numbers.
What else are they for?
They're also meant to be used to illustrate scientific laws verbally.
Ah, so you need to understand the concept behind the equation, not just how to calculate with it.
Exactly. It implies a deeper level of understanding connecting the mathematical representation to the physical principle. Conceptual fluency.
That makes sense. And beyond the data sheet, what other underlying skills are they assessing? It feels like there's more to it than just the physics and chemistry content.
Absolutely. The syllabus is quite explicit about the scientific skills that are assessed right alongside the content. Things like basic arithmetic and algebra are assumed, of course, using calculators, scientific notation, solving equations, but also things like unit conversion, knowing your metric prefixes like nano, micro, kilo, giga, and converting between common units for mass, volume, etc.
Standard lab skills, basically.
Standard scientific literacy skills, yes. And then there's a big emphasis on mathematical relationships and graphical representation. Can you identify independent and dependent variables? Can you look at a data table and spot a trend? Can you choose the right scales for a graph?
And interpreting graphs, too.
Critically important, understanding what the slope or the area under the graph means. Like knowing the area under a velocity time graph gives you displacement. That's a core skill they test.
Right, that comes up all the time in physics.
hmm And finally, there's a whole section on skills for practical investigations. Formulating a hypothesis. Designing a simple experiment, thinking about controls, carrying out procedures safely, recording data accurately with the correct units.
So the whole scientific method.
Pretty much. Analyzing that data, distinguishing between precision and accuracy, spotting potential errors or bias, and sometimes even developing a simple mathematical model from your experimental results.
It's not just about the physics concepts then, it's about being a scientist. They give you the toolkit with the data sheets, but they expect you to master these broader skills too.
That's a great way to put it. And it raises that question, why these specific skills? It's because knowledge isn't much use if you can't apply it or verify it. Being able to design an experiment or critically analyze data from one is just as vital as knowing Newton's laws. It's about preparation for, well, real world science and problem solving.
Which brings us back to that ongoing assessment piece, the SBA. You said it's 25%. That reinforces the practical side, doesn't it?
It absolutely does. That 25% waiting for the school-based assessment isn't just an afterthought. It's a core part of the philosophy. It ensures you're continuously engaged, and importantly, it allows for the assessment of practical skills and longer-term projects in a way that timed exams just can't.
Right. You can't really assess designing an experiment well in a 3-hour written paper.
Exactly. So for grade 12, the minimum SBA requirements are quite specific. You need to do at least 2 practical investigations, one focus on physics, one on chemistry. Each should take a minimum of 2 hours.
2 hours per investigation, okay.
And these practicals contribute 30% of the total SBA mark. The guidelines even mention using simulations if needed, perhaps for reasons like social distancing or lack of equipment.
That's practical. What else is in the SBA?
Then there are 2 controlled tests, again, one for physics and one for chemistry, minimum 40 minutes each. These make up another 30% of the SBA marks. Sometimes mid-year exams might fulfill this requirement.
Okay, tests and practicals.
And the final and largest chunk of the SBA comes from the preliminary examinations. These are basically mock final exams, 2 papers, physics and chemistry, 3 hours each, just like the finals. These contribute the remaining 40% of the SBA mark.
So prelims count towards the SBA, not just practice for the final.
That's right. It really underscores the importance of sustained effort and performance throughout the year. It's not just about those last exam days. The entire year builds towards that final assessment. It prevents cramming and ideally fosters that deeper, more integrated understanding.
It really sounds like a comprehensive system. Now, we've talked about the structure, the cognitive levels, the skills. Maybe we could dive into a couple of specific physics topics mentioned in the outline, just to see how these ideas play out in practice, like kinematics.
Sure. Kinematics, motion in 1D, is that big 25% chunk we mentioned. It starts with basics, like distinguishing vectors from scalars, displacement versus distance, velocity versus speed. You need to be really clear on those definitions.
Right, the direction matters.
Crucially. Then there's vertical projectile motion objects thrown up or dropped. Key things there are realizing acceleration due to gravity is constant, downwards, and understanding the symmetry time up equals time down to the same height.
Okay.
And a huge part of kinematics is graphical analysis, interpreting and drawing position time, velocity time, and acceleration time graphs. Understanding that the gradient of a position time graph gives you velocity, the gradient of velocity time gives acceleration.
And the area under the velocity time graph.
Gives you displacement. Exactly. Those graphical skills we talked about are absolutely essential here.
Makes sense. What about Newton's laws? That was another big area.
Yes, Newton's laws and their applications. First, you need to identify all the forces acting on an object. Weight, normal force, friction, static and kinetic, applied forces, tension and ropes. And drawing correct free body diagrams is non-negotiable. That's step 1 for almost any problem.
The diagram helps visualize everything.
It's fundamental. Then you apply the laws. First law, inertia. Objects stay at rest or constant velocity unless a net force acts. Think about why seatbelts work.
Right.
Second law is the big one computationally. Fent, maybe a may. This is used to solve problems for single objects, objects on inclined planes, objects in elevators, even systems of 2 objects connected by a rope, perhaps over a pulley.
Lots of applications there.
And the third law, action-reaction pairs. Equal in magnitude, opposite in direction, acting on different objects. People often forget that last part.
Ah, right. The force the car exerts on the truck and the force the truck exerts on the car.
Exactly. That brings us nicely to the next related area, momentum, impulse, work, energy, and power.
Okay, how do those connect?
Well, linear momentum is defined as PMV, and Newton's second law can actually be stated in terms of momentum. The net force equals the rate of change in momentum. This leads directly to the principle of conservation of linear momentum in isolated systems. Total momentum before a collision equals total momentum after.
For collisions and explosions, right?
Yes, and distinguishing between elastic collisions where kinetic energy is also conserved and inelastic ones where it isn't. Then there's impulse, J, which is the net force multiplied by the time it acts,
Like hitting a baseball.
or airbags in cars. The key relationship is that impulse equals the change in momentum. Airbags increase the collision time, reducing the force for the same change in momentum. Real world physics.
That's a great example. And work, energy, power.
Work done by a force is W affects cos.
Yeah.
You need to understand potential energy, gravitational usually, and kinetic energy. Mechanical energy is the sum, PE plus KE. We have the law of conservation of energy. Total energy is always conserved. And under specific conditions, no friction air resistance, conservation of mechanical energy.
Okay.
There's also the work energy theorem. The net work done on an object equals its change in kinetic energy. When it, very useful shortcut sometimes. And finally, power the rate at which work is done, PWT, or energy is transferred. Also useful is PFV for constant force and velocity, and concepts like efficiency tie into this.
That's a lot packed into that section. Really shows how the concepts build on each other. Maybe one more. How about something from electricity and magnetism, like electrodynamics?
Okay, electrodynamics focusing on electromagnetic induction and AC generators. It starts with the concept of magnetic flux, which is basically the amount of magnetic field passing through an area of EV. And magnetic flux linkage is just that multiplied by the number of turns in a coil.
Flux, like flow.
Kind of, yeah. Magnetic field lines flowing through a surface. The crucial part is Faraday's law of induction. If you change the magnetic flux linkage through a coil, an electromotive force, basically a voltage, is induced. And the faster the change, the bigger the induced F.
So changing magnetism creates electricity.
In essence, yes. And Lenz's law tells you the direction. The induced current flows in a direction that opposes the change in flux that caused it. It's all about conservation of energy, really.
Opposes the change.
Right. Applications here are things like electric generators and transformers. The guidelines mention AC generators, specifically how they convert mechanical energy into electrical energy, using slip rings to get alternating current. And touches on why AC is useful for power transmission. You can step up the voltage using transformers, which reduces the current for the same power, minimizing energy loss in the wires.
Ah, the economic advantages.
Exactly. It connects the physics principles to real-world engineering and economics.
And maybe just briefly, that last physics topic, photons and electrons, the photoelectric effect.
Right, the photoelectric effect. This one is fascinating because it's where quantum physics really starts to show up. First, the basics, the relationship between the speed of light, c, frequency, f, and wavelength, which is c phi, and the idea that light energy comes in packets called photons with energy E, H, F, where H is Planck's constant.
Mhm.
They also introduced the electron volt EV as a unit of energy.
Okay, light as packets of energy.
Then the effect itself. Shine light of a high enough frequency onto a metal surface, and electrons, photoelectrons, get ejected. This was a puzzle for classical physics, which saw light only as a wave.
Why was it a puzzle?
Because classical wave theory predicted that any frequency of light, if intense enough, should eventually eject electrons. But experiments showed there's a minimum frequency needed, the threshold frequency, S0, specific to each metal. Below that, nothing happens no matter how bright the light.
Ah, the frequency mattered more than the intensity, in a way.
Precisely. And the energy of the ejected electrons depended on the light's frequency, not its intensity. Increasing intensity just ejected more electrons, not faster ones. This led to Einstein's explanation using photons. One photon gives its energy to one electron. The electron needs a minimum energy, the work function, W00 is H as 0, just to escape the metal. Any extra energy becomes the electron's maximum kinetic energy, EK max. So the photoelectric equation is E equals W0 plus EK max, or H equals HS0 plus EK max. It beautifully explains all the observations and was key evidence for the particle nature of light and quantum theory.
That really brings together energy, light, and the quantum world. What a fantastic example of how these concepts develop.
It really is. And you can see how assessing it could range from just defining work function, level 1, to explaining its significance for quantum theory, level 4.
What a journey. We've really dug deep into this assessment structure for physical sciences. We've seen the balance between the two big exam papers, physics and chemistry, with their specific content weightings, and that really significant 25% chunk coming from the school-based assessment. And we explored those cognitive levels, realizing it's not just about remembering facts, but moving through comprehension, application, analysis, and right up to synthesis and evaluation. That's where the real scientific thinking happens.
Hmm. And the importance of those underlying scientific skills can't be overstated. The mathematical tools, graphical literacy, and the practical investigation skills, they're all woven together.
Absolutely. It feels like this whole structure isn't just about testing knowledge for an exam grade. It's about building a foundation for critical thinking, for problem solving, for really understanding how the physical world works based on evidence and rigorous methods.
It's a blueprint for developing scientific capability, you could say.
Definitely. So, as we wrap up, here's something to think about. How might approaching any new complex subject, not just science, anything really, with this kind of structured deep dive mindset, breaking it down by its core content, thinking about the levels of understanding required from basic recall to deep synthesis, and identifying the essential underlying skills,
Yeah.
how might that transform how we learn well beyond any classroom?